To everyone, how nanomaterials could be good or may not be good for battery applications. And that is the reason I put a title, Fate of Nanostructured Materials in Rechargeable Batteries. Can you see the second slide now?
Yes, sir. Yes.
Okay, that
Please
means
continue.
we are together. Good to hear that. So the outline of this presentation is very simple and straightforward. I will be talking about what we do, what are the unique ways to make nanostructured material for a variety of application that includes your color application, ceramics, antennas, and so forth and so on. But the main focus is lithium-ion batteries today. There are simple ways to make nanomaterials such as sol gel synthesis that you can see here. Let's use the pen. Then we will also figure out that what are the battery research challenges and how we can make it simple in a way that we can solve all the challenges together and not one by one. Otherwise, typically we try to solve one problem and create many others. That is not the way to solve any scientific challenge. So we will be talking about that. And eventually, how can you make high energy density batteries? Those batteries can be in your cell phone or laptops for a longer time without further charging. And with that, we will conclude. So my group here at Purdue University works on a variety of things. For example, lithium-ion batteries are there in our cell phone, laptops, and even electric vehicles nowadays. So we focus on making them safer. Not necessarily they are safe, as you know that anything that carries the energy or energy density, that energy always want to release. And we have to be careful that it is released in a proper way, otherwise it can be catastrophic failure. So we have to be careful. The next generation batteries, we call it as sodium-ion batteries, where sodium is abundant and inexpensive and can be utilized in the batteries. Those could be stationary batteries where you can capture solar energy and thermal energy and many tides energy. Those energy can be captured in sodium-ion batteries, which will be slightly bigger than lithium-ion battery. As you know that sodium is beneath lithium, and that is the reason that it becomes slightly heavier because of higher atomic mass. Beyond that, people are also talking about potassium-ion batteries. So we also started research work several years ago, supported by National Science Foundation, where we are the first one to figure out, are those batteries going to be safer? If they are not safe, there is no point developing something new. So our main aspect is to study the safety features of the batteries. So apart from nanomaterials or micron-sized materials or new materials, is the battery safer than current batteries? Then there is a point utilizing such battery materials and utilizing the batteries in future. There is also another type of battery called as lithium sulfur batteries. Those are also getting very popular nowadays because of high energy density of sulfur, and lithium metal itself can go inside the battery. So there are a variety of things are happening in the lab. As we heard that solid state batteries also can be prepared utilizing glass material, and we do use glassy material as an electrolyte in between anode and cathode, and eventually those batteries also can be made and utilized. Actually, solid-state batteries are all safer than all these 3-4 types of batteries because there is no liquid. In these batteries, there is a liquid electrolyte which has a tendency to catch fire above 60-70 degrees Celsius. Therefore, those batteries are not safe, but the solid-state batteries, what Dr. Jaishankar was talking about, those batteries would be safer than current batteries. However, they have their own inherent problem, such as lithium does not want to diffuse back and forth. We call it as shuttling of lithium during the charge and discharge. So those batteries are still under development, but at some point we will be able to see solid state batteries in the market. Now, let's go back and see whatever we are talking about nanomaterials. Actually, they are there forever. For example, the physicist Richard Feynman said in one of the meeting 1959 itself that there is plenty of room at the bottom. What does it mean? We know those are the elements in the periodic table, we can utilize that. But when they become smaller and smaller, typically the particles become less than 100 nanometer. Half of the atoms of the particle are on the surface, and that allows you to get a unique feature out of that material. And that is why people were believing the physical and chemical properties of the material will be different if they are in the nano size. Therefore, we would like to put the chemistry, engineering, and physics together in order to make these nanomaterials work. Not necessarily they are creating good outcome every time. For example, in batteries, the nanomaterials are not that great. And the reason is the electrolyte sitting inside the battery has pH 2, highly acidic, and that can corrode those small particles. So initially they can behave very well, but with time, the capacity could degrade very rapidly. And that is the reason that we have to be very careful what we are using, where we are using, and how it is going to be applied. So here the white spot dotted here, those are the elements my group has studied so far, including the rare earth metal, getting the red emission and blue emission and green emission. So my group used to work in a variety of things in past, solar cell, lithium-ion batteries, photonics, and many other parts, but currently we focused on only energy storage devices. So if we can manipulate those individual atoms, so the part it has to play is with chemistry. And if we have a good chemistry, strong background in order to make and manipulate the atoms to either order the nanoparticles or make a architecture out of it, we will be able to get unique properties from those nanostructured materials. Since we will be talking about batteries, I would like to highlight that there are two kinds of batteries we do see everywhere, and we call them as a primary battery or secondary battery. The unique difference is secondary battery you can charge and discharge again and again. The primary batteries are made only to discharge. For example, if you have a wall clock in front of you, you put that AA battery or AAA battery in that, and it only discharges, provides the current to the clock, and at some point when it is completely discharged, it stopped working. So it is an irreversible battery chemistry. And we are allowed to throw those batteries in the dustbin because the chemical inside, typically manganese oxide and zinc, those are not really harmful. And that's why we are allowed to discard such batteries, and we may not have to have the recycling of those batteries. However, the life of those batteries are very small or short, because as soon as you make those batteries in the industry, they start discharging, and eventually, once they discharge, you cannot utilize that anymore. And they cannot be a storage device. They are just discharging. So the storage we need, for example, from sun, we collect the energy and put it in the battery, but it has to release again. The primary batteries are not useful there. We call it as dry cell because it doesn't have too much electrolyte. It just makes the anode and cathode wait to transport the ions. On the contrary, the secondary batteries are opposite. They are reversible. We are allowed to charge and discharge. The life is pretty good. As you can see that your cell phone batteries minimum can survive up to 2 to 3 years. That is 1,000 charge and discharge cycle approximately. And that's why we can use them for the storage devices, and we are allowed to recharge them. But you may or may not be aware of the fact that the primary batteries you should never try to charge because the chemistry there is not made to charge, and those batteries could explode if you try to charge in your charger. So never charge the primary batteries in the charger because the chemistry is not reversible. Thermodynamically, they will increase the heat because you are putting the current inside, and eventually it can explode. So there are multiple type of secondary batteries that include lithium manganese oxide or lead acid batteries that is helping to turn on your car. Niked batteries were very famous in our cameras. Our parents were using cameras that used to have that big battery. Nowadays, even that is not there because of the lithium-ion batteries. Now, what are the advantages to use lithium-ion batteries in your cell phone and laptop? As you can see that lithium is the lightest element in the periodic table. Before that, there is hydrogen and helium, which are gases. This atomic number 3 element is the lightest and also can hold a huge amount of energy. And that is the reason we are using it in your cell phone and laptop. It also produces very high voltage that is required in order to have high energy density, such as nickel cadmium batteries, which used to have a memory effect. Namely, if you discharge the battery up to a certain extent, it will used to remember, and next time it will discharge from that place or only charge up to that certain potential. So there was some issue with the nickel cadmium batteries that is not there for lithium ion batteries, and that's why they are very popular everywhere. The discharge for the lithium-ion batteries could be slow or fast based on the need, and it also provides you longer shelf life. However, as I mentioned before, it uses flammable liquid inside the battery that could lead to thermal runaway of the battery, eventually fire and explosion. There is a solid electrolyte interface formation in the battery that could also lead to some catastrophic event once it is degraded. So batteries also does not like either high temperature or low temperature. For example, now here in Indiana, we have snow outside. And in India, in summer, it could be very hot. The electrolyte, since it is liquid, in hot temperature, it tries to evaporate, and in cold temperature, it tries to freeze. And that's why the ability to shuttle lithium back and forth is very weak in high or low temperature. They just like environment inside the room, let's say 25 degrees Celsius, and at that temperature, they work good. So there are disadvantages of these lithium-ion batteries, apart from there are advantages. So we have to figure out with the material science, what are the materials one can use in order to make those batteries better. So since you are all beginners, I would like to provide some history of the batteries. They are not old, actually. The batteries came to market in 1991. That might be the year we are all born. And since then, in 30 years, the batteries are everywhere. Namely, we are 7.77 billion population in the world, and we are holding more than 15 billion batteries in our pockets and purses and electric vehicles. So in 30 years, really remarkable thing happened, and the battery market really exploded because of the need. And that's why you started seeing the batteries everywhere in the electric car, your laptop, and cameras and cell phone. So I used to work at Argonne National Lab, as mentioned before, where former President Obama came, and he was saying that we should develop the batteries. That was back in 2008. And he understood what is the significant need of the battery science and technology. A very famous electric vehicle, I am sure that there might be some vehicles in India now that is made by Tesla. As you can see, that whole vehicle has a battery pack, and that batteries are located underneath here as a chassis of the electric vehicle itself. And there are thousands of batteries sitting here in order to drive you 400 to 500 miles per charge. That means really a huge amount of electricity is stored in this area. And because of that, we have to be very careful. Safety is a paramount. Otherwise, exactly you are sitting on the top of bomb here, which is holding such a huge amount of energy. The batteries are typically made by Panasonic, where it is called as 18650. This is the engineering name. 18 means it is 18 millimeter wide, 65 millimeter tall, and it is a cylindrical battery. That's why it is called as 18650 batteries. And there are around 9,000 batteries sitting in your car. Now, just imagine the engineering way you have to really ask those batteries to work together. Even one of the battery in that 9,000 doesn't want to charge or discharge properly. It is connected to the neighboring batteries. So we have to be very careful electronically in a way that those batteries communicate with each other, or if the battery from one of the pack is bad, then selectively we take that out or stop taking the advantage from that, and the remaining battery pack should work. So that's the challenge for engineers to make sure that batteries are working safely with us. In 2019, this technology got a Nobel Prize in chemistry, and that is developed by John Goodenough. All of them are alive. He's in Texas, New York area. Professor Stan Whittingham is there, and Professor Yoshino is from Japan. So the initial battery materials were developed and tested in America, and then Japanese scientists put them together in front of graphite as an anode and lithium cobalt oxide based cathode, and eventually the real battery could work, and that came to market in 1991. So it is really worth giving a Nobel Prize, giving worth technology that touches every life on this earth. Let's see what are the challenges still remaining in order to develop those batteries and what we are doing to mitigate some of them. For example, the cost of the batteries are very high, and therefore, when your batteries are going down, instead of changing the battery, you change your cell phone itself. As I mentioned, they are not safe. We have to continuously go on making them safer as we are holding a huge amount of energy. The life of battery is also very limited, typically around 5 years or so, but our target is up to 15 years. As you can imagine, all your vehicles running on the road, they have typical lifespan of 15 years. If we have electric vehicle, we also assume that it should stay for 15 years. Otherwise, we put significant amount of investment and it is not working there for you longer time. So the cost benefit is not good there. The battery, as I mentioned, does not want to work at low and high temperatures. So we have to have a nice materials and electrolyte developed that allows to work at low temperature. For example, when you are going on the NASA and there is a shuttle there that needs some energy when it is on Mars. For example, NASA's application is Mars. Anybody want to go on Mars? What is the electricity and how to store them? So we have to have a device that works at significantly lower temperature. For example, the temperature could be as low as minus 120 degrees Celsius. So at that temperature, your battery should be operational. So we have to have the electrolyte that really work at that temperature. Now the newer problem is coming that we do not know how to recycle those batteries effectively, and we are trying to find solutions for recycling. Otherwise, we are creating a huge amount of debris. And if we do not solve all of those challenges together, according to me, our future could look like a broken glass. And the reason is we create something good, at the same time, we are creating too much bad to the environment and earth, just like the plastic waste all over the world. We are facing the problem that how to recycle or upcycle the plastic, and nobody knows it effectively. We know how to make different type of plastics, but not knowing how to recycle them. Similarly, batteries is the way where we know how to make and use the batteries, but it is very difficult and not economical to recycle them. Now let's go to the material science and nanotechnology that we are talking. So there are various ways to make nanoparticles. As previous talk was mentioning that glasses can be made in nano size and can be utilized. So we have hydrothermal system, sol-gel system, we put heat and try to evaporate the material and it comes back. Solid state, it is typically a very high temperature process. Glasses are prepared at higher temperature. Then we have a template type of process, difficult to scale it up. And this mechanochemical milling, we call it as ball milling. So there are a variety of requirements to all of those techniques, and sometimes they have limitations. For example, they can produce very small amount of yield. So we can produce it, but if it is not scalable, it is not useful for industrial application. So we have difficult to handle some of the hazardous material that can make nanomaterials. And sometimes it is not reproducible. One scientist can make, but other cannot make it because of the change in parameter or handling parameters. So all of the processes has their own advantages and disadvantages. So considering all of that, long back, I was considering slightly different 4 new approaches or somewhat improved approaches. For example, the microwave you are using at home, which has the ability to superheat things. For example, if the boiling point of water is 100 degrees Celsius, when you put a cup of water inside the microwave, it does boil at 108 degrees Celsius. The heating in the microwave is in the opposite fashion compared to all your traditional heating. So typically the heating is inside out in microwave, and in traditional heating, the heating is from outside in. And because of that, there is no point where the boiling will start. And that's why water gets boiled at higher temperature in the microwave. Electrospinning, where you can use very high current, up to 15 kilovolt. It is very high current. At that current, you can charge the material and pull it to the other side. Every second, you can make 5 to 6 meter long fiber that can be nano size. Here I am demonstrating that gold nanowires were produced in this electrospinning. Previously, people used to make polymers, but for the first time, we also tried to make some inorganic material, metallic one, and they could be pulled. And those I used to use, or my group used to use for solar cell application as a current collector. Sonochemistry, where the ultrasound is used in the medical field, everybody knows that. We also try to put that in order to make nanoparticles back in 2000 in a way that they are really, really small. For example, if you have a gold nanoparticle that is only 1 or 2 nanometer diameter, which will have the melting point of around 200 nanometer. In contrast, the bulk gold melts at 1000 degrees Celsius. We came up with another completely new approach. I call it as dry autoclaving, where you don't need too many sophisticated things. You just need a chemical precursor and a reactor and a heater. And once it is there, you heat it up and you allow the different elements from that chemical to work with each other and eventually make a unique form of product that can be a core shell material. Here, carbon is the shell and vanadium oxide is a core, which is a very good material for battery application. And then a variety of application can be studied. So this is the process where you have a reactor, you load the precursor inside the reactor, and that precursor, you heat it up. If the precursor has, for example, 3 elements from the periodic table, making this allyl triphenyltene, once you heat it up, based on their thermodynamic and chemical stabilities, they are going to go to the critical phase. Namely, the phase could be liquid gas, gas-gas, or solid gas interaction. And then you allow it to cool down, you get a product. And that product is a dry powder. In this particular case, we got tin particles, we got carbon shell, and we release the hydrogen. So you can see that the thin particle is only 2 nanometer diameter, and there is a carbon layer around it. So such a nice small particle can be made in a core shell architecture. Now you might ask, why do you need core and shell? The thin particle, if it is really small, it get oxidized, react with air, and make tin oxide. The tin oxide has different properties than metallic tin. So we wanted to have that metallic tin in a nano size, then you have to protect, and that protection is provided by this carbon layer. Carbon is very stable, as you know, and that is useful to protect that material, and you can still get the properties from tin. That doesn't mean that we are not taking the properties. However, to make materials with this reactor, we have to design a special reactor because it is a high temperature, high pressure reaction. So the reactor was holding up to 80 cc capacity, up to 2000 psi pressure, and it can go up to 800 degrees Celsius. But with that, then we have several advantages to use this unique type of reactor that can make the materials reproducibly. Only one single step has to be used. No further cleaning is required. We did not use any solvent or catalyst, and really it is environmentally benign process because we do not create any byproduct, and it is ready to go at variety of application. So this unique process made almost everything from the periodic table, and that is the reason I was highlighting some of the elements in the periodic table, where we could make very unique sulfides, tungsten disulfides, which is a very nice material for lubrication. One can make phosphide-based materials, which are very stable. The tungsten carbide-based materials typically can be prepared around 1600 degrees Celsius, but in this particular case, it was required only 800 degrees Celsius temperature. And the reason was you start playing with the atoms where the small amount of energy is required. Borides and nitrides, so actually it was so versatile, one can make any material that you would like to use. Now one can see that variety of ceramic materials with unique architecture can be prepared. For example, photoluminescence property. You were watching in previous talk, the glasses give you different properties because of the elements used. For example, zinc oxide has certain properties which can give you yellow color or green color. Europium oxide or europium oxycarbonate, this was the first molecule fabricated with this unique technique, which gives you very strong red color. Europium oxide is known for hundreds of years, but europium oxycarbonate was not easy to make. This reactor could make it. We could also make superconducting material, the materials for photonic applications such as solar cell, battery application. We also try to store hydrogen in those materials. And it is also good for environment to upcycle plastic. Upcycling means you take totally useless things such as plastic and make highly valuable products such as those spherical carbon particle or carbon nanotubes out of this waste material, utilizing this autogenic reactor that we developed. Now, let's talk about how the lithium-ion battery works for a few minutes, and then we can move and see some of the material work for the battery application, and then you can go for your dinner. So typically, there is a cathode. We call it as a positive electrode and negative electrode. Now, in the cathode, there is a lithium ion sitting. That's why it is called as lithium metal oxide, and the anode is typically graphite. When you try to charge the battery, what happens is this lithium ion gets split from this lithium cobalt oxide, and then it moves or travels through the separator to the counter electrode. In the meantime, the electrons are going from outside and combining lithium metal or lithium ion plus carbon and making LiC6 structure. And during the discharge, when you are using the cell phone for playing the video, the electrons are knocked out, and those electrons you are using for playing the video, and the lithium ion is going back to its parenting molecule. And once it happened, the battery is getting discharged, and then you have to charge, put the current, bring the lithium in between the carbon layers. So this has to happen for hundreds or thousands of times. That is the way the battery can stay there for longer time. But as you know that there is nothing 100%. We always lose some energy during the transport phenomena. And that is the reason when you buy the brand new battery, it works very good. And with time, the battery go on fading its capacity. Are you still with me? Hello?
Yes, sir.
No sound. I thought you all of you disappeared.
No, we are interestingly listening to you.
All right. So you see the variety of anode and cathode materials can go inside the battery here. And because every company can use the materials of their choice, there is a problem in recycling. For example, I have a company where I use titanium dioxide coated with carbon as an anode and this cathode. But somebody can come up with this material as a anode and cathode. In that case, when you try to recycle the battery, there is a mix of so many things. Which process we can use to recycle, either precipitation or whatever. But in that case, you have different elements, they have different properties. And recycling is becoming too complex. But in this talk, I'm just going to show you the ability that can be, those unique nanostructured material can be used with this autogenic reactor. As everybody believes when they see something. So there are a variety of materials were made with this technology. We will focus only on one because of the time and not to talk about others, believing that we did made it and studied them. Not only anode, but also cathode materials in the market, those were also made. Let's focus and see how can we make one unique material with one single precursor without using any solvent in a lab. For example, TiO2 as an anode material, I showed in the cartoon, the graphite was used as an anode, but this material also can be used as an anode material. The titanium is used in the solar cell, which is a semiconducting material. So there should be a conductivity, and that is the reason we add a small amount of carbon layer on the top of TiO2, where the electron can hop effectively, and we could create an original core shell architecture that will give you enough capacity, and at the same time, the batteries could be safe. So to enhance the conductivity of titanium, we use the small layer of carbon, and with that, we will be able to synthesize the material, and eventually it can be useful for the battery application as an anode material. As I mentioned that we need a single precursor. This is the simplest chemistry one can do anywhere in the world. Titanium oxy carbonate or one complex precursor that has carbon, hydrogen, oxygen, and titanium. And our goal is to make TiO2 gently coated with carbon. So when you heat it up at higher temperature, you are getting a variety of things up in a critical phase. That TiO2 can form a TiO2 that you need as a ceramic, but carbon comes and separates from TiO2 and say that I am not going to talk to you anymore because my stability is different than yours, so I will stay away from you. Then TiO2 condensate and make a nuclei. Afterwards, carbon comes around it and hydrogen stays as a gas. Eventually, you get a core shell architecture, and this is a unique product where you can utilize it for the battery application. Now you see this is a very small tiny particle around 5-6 nanometer. There is a small layer of carbon around it that gives you conductivity. This particle now started talking to other particle because there is the interfacial layer that connects to particle. And just having nanoparticle is not enough because they have a huge surface area. They can have a high reactivity and they can react with electrolyte and bring the battery performance down. So this connection could make millions of particles together. and they are sitting next to each other, making sure that they are friends of everyone, and at the same time they are allowed to charge and discharge via this carbon layer. So the unique architecture is very difficult to make, as you cannot see even those atoms. To see those, we have to resolve the material up to 150,000 times. So how can you manipulate those atoms in a reactor? So we have to come up with a unique approach to design such architecture, what we did in past, and that's why these materials worked very well in the battery application. Those are all characterization tools. As you can see that there is a Raman spectroscopy, X-ray diffraction spectroscopy, and that gives you different spectrum to tell you that is the material pure or not. If it is pure, it is going to work in a unique way. If it is impure, it will have slightly different properties. So Raman is talking here about disordered carbon and graphitic order inside that carbon that we saw quoted on the TiO2 particle. By the way, Raman spectroscopy is based on the C.V. Raman, Indian scientist who got a Nobel Prize for its scattering effect in 1930. So we should be all proud of him. And all of us should think that after that, we never got any Nobel Prize in science. So maybe this is the time that you guys should think hard. How can we do something unique that would lead to Nobel Prize for India? Now, this material looks like this, or the structure of this material allows to have the lithium in and out, and that is what should happen during the charge and discharge. And that is the way you will be shuttling the lithium back and forth. That is why its structure is really important, how the structure is aligned without impurities so that lithium shuttling can happen. So this is electrochemical performance, where you have a lithium metal as one of the electrode and TiO2 coated with carbon is other electrode, and you charge and discharge, charge and discharge. Initial capacity is around 200 and it continuously go on fading. It doesn't stabilize the capacity. Apart from there is a carbon shell that helps to shuttle the lithium back and forth. But with one part synthesis, one can make a unique material that does cycle. And that is the reason when you make the battery in the first day, it works good. And with time, the capacity fades. Although you charge it, it doesn't give you too much charge back. We call it as full cell. Full cell means there is a unique type of cathode. The cathode holds lithium-ion that sits inside the battery, and then you couple that with your anode. That's a real battery. You can see such batteries in the market, where you can get reasonable capacity for lots of cycle during the charge and discharge utilizing this new material. Now, I will give you another quick example of how the nanostructure material works, and then we will wrap up, and I will take some of your questions. So here is another example where we made tin oxide nanoparticles. We were talking about tin before, now tin oxide nanoparticles, how they can help you to make the batteries. Those batteries can work very well for the energy storage application. So we again took a single precursor of tin, we put it in the water, we heat it up, we got very nice tiny nanoparticles of tin oxide. When we dried them off, removed the water molecule out of it, we got very nice shiny gold-like tin oxide particle. And those whitish tin oxide particle, when you sintered them, they try to come together and make a very nice architecture such as a garland. So there is some space available in between particles. And that is the beauty of this unique work, that space was required. Namely, when you take lithium and charge and react with tin, the material has the ability to expand up to 300%. And those cavities can accommodate that expansion. And that is the reason we purposefully created an architecture where those cavities are created. And those cavities can accommodate that expansion, eventually making sure the battery is working good for a longer time. We did some characterization, which we call thermogrammetric analysis, that tells you how much water is there in your material. and as a function of temperature, you can get rid of it and keep the product in hand that you need. Similarly, we did other characterization. X-ray tells you the purity of the material. The broader the peak, that means smaller the size of the particle. If it is sharp, that means particle is really bigger. And again, how the X-ray is interacting with the particle, based on that this diffraction pattern is created. The surface area of the material is also important. As you make smaller and smaller particle, the surface area will be larger. But at the same time, the battery is becoming light in weight, but also big in volume. You don't want the battery too big in volume. You want battery also small. So the surface area measurement becomes important. Here, take-home message is, when you have the material only gently dried at 100 degrees Celsius, the surface area was high. As you heat it up to 400 degrees Celsius, the surface area goes down, but there are cavities generated around 4 to 8 nanometer, and those cavities were very important for us to expand the material. This is a scanning electron microscopy picture where you can see those particles are accumulated. They are very tiny in size. That is going to give you the property. What you are seeing here is the electrochemical performance. In previous titania case, you were seeing around 200 milliamp hour per gram capacity. Here the capacity is almost 3 times higher, around 500 milliamp hour per gram, and this battery cycles for a long time. If you do not have the architecture made, then battery dies much faster. Even the commercial material, which is very expensive to get, did not work very good. The capacity is close to 0 in 100 cycles. That means within 100 days, daily charging and discharging, the battery is dead. That's why the nanomaterials could be bad or good for the battery application based on how you design them and how you are utilizing them. This impedance spectra tells you about the conductivity or the resistance in the system. As you can see that the ordered tin oxide particle has a low resistance. This half circle is very important. If it is smaller, that tells you the impedance or the frequency. Smaller the better. On the contrary, the commercial had the bigger channel and the lithium diffusion was a difficulty. And that is the reason the battery could die faster. These are the charge rate. You can see that one can charge in 2 hours or 6C, that is 15 minutes of charge and discharge. 1C is equal to 1 hour of charging, 1 hour of discharging time. Even with very fast charging and discharging time, you still get a reasonable capacity out of such nano architectured material. And that's what the title says, the fate of material. It can be the same material, but if it is not architectured well, it can die rapidly. We open up the battery and see what happened inside the material. And what you can see that the electrode which we had inside the battery, which had some cavities, and those cavities are still there after cycling. That means that architecture does not degrade or decompose because of continuous charging and discharging. So there are a few more examples, but instead of continuing to talk, I will be happy to take your questions. So these are the unique architectures were developed and studied, and all the batteries were cycled. Very unique architecture can be made with the reactor that I showed in the beginning. But I should say that I will stop here and take your question. Just concluding the whole talk, saying that if you engineer the nanomaterials, as your whole conference is on the nanomaterials, so just making nanomaterial is not enough. You have to engineer those materials in a way that sometimes you need core shell so you can protect the material. Sometimes you have to make it nano size, but architectured, sinter them together so that they have electron hopping property. Sometimes even the defective elements could be providing you unique luminescent properties. So based on the requirement, you can design and make the materials, and that is the way you can define the fate of those nano-architectured material in your typical device. With that, I would encourage you to join us at some point to become a graduate student, that is a PhD student, and try helping us to develop the new technologies that could be battery technology or ceramic technology or glass technology to make our world better and our next generation better with the scientific development that we are doing today. With that, thank you very much for listening to me, and I will be happy to take your questions. Thank you.
Thank you, sir. So the first
Do you have
question
any
that
questions?
comes is, can we use the domestic microwave oven to synthesize nanoparticles?
Yes, one can use the domestic microwave oven to synthesize the nanoparticles. However, the modified microwave oven is useful to utilize, and the reason is in the microwave, everything, any chemical reagent that you can put it inside. For example, there was one IIT Hyderabad student was in my lab for 1 year last year. We were taking plastic waste, polyethylene terephthalate bottles, putting in the ethylene glycol, heating it up. Within a 1 minute, you can convert polyethylene terephthalate to sodium terephthalate. So the chemical reaction happens in 1 minute. But since the microwave put too much energy, things start evaporating. And you do not want to inhale those evaporated materials. Sometimes it could be good, sometimes it could be toxic. So we used to have a reflux system connected to the microwave. And that is the way we could generate a nice product. The other way, there was a teen precursor. We took it, we put it in the microwave. We could make nanomaterials within a minute, actually 30 seconds or so. But again, the material, the metals, you cannot put it in the microwave. So you have to be very careful what you are preparing, how you are preparing, and what could be the outcome. So you should understand the chemistry. Simply should not throw anything in the microwave. It can be catastrophic and it can be dangerous. So be careful what you are doing. But indeed, if you have a hood system where the ventilation is there, the gas that goes outside, you might be able to use domestic microwave. But the modified one is better because then you have the abilities to tune the environment, collect the vapors, and not to have the bad things that could happen.
Thank you, sir. There's another query. Did the core and shell have different absorption peaks in the UV visible spectrum? If so, which peak is to be used for calculating the band gap energy?
So it is very interesting. If you are talking about the TiO2 and carbon coated or zinc oxide, and if zinc oxide is coated with carbon, as you can see or you understand very well, the carbon is a good absorber. It absorbs all kinds of energies. So actually, your all spectrum can be quenched. So having the carbon shell is not the best idea. But if you have a zinc oxide material that is produced under the impurity of zinc and carbon and hydrogen, which are reducing atmosphere, then you get a ZnO minus X. When you have something like that, then you tune the property of your zinc oxide in a way that instead of getting one strong peak, you are getting yellow color and green color and slightly other color. So the defects can tune the property itself of the material. But having the complete core shell property for luminescence purpose may not be very useful because you change the spectrum and may not get anything when you excite at any wavelength. The emission wavelength you may not get because it is quenched and there is no transition happening.
Good evening, sir.
Yes.
Hello. You are prepared that from the synthesis process that is called Solgel spin coating, I think. Solgel process, that is SNO2 interconnected particles. So
Yes.
as we keep on decreasing the surface, what is that nanoparticle size, the surface to volume ratio is increases.
Yeah.
Then how do you connect that, correlate with that nanoparticle surface area with that lifetime of the batteries?
So you see what happened, the Solgel synthesis process that I showed quickly, where
Yeah.
the chemical precursor is thrown inside the water, then eventually it made a nuclei. And once you remove the water, you have those nuclei. Let's say those are 10 nanometer particles. Once you dry them off at 100 degrees Celsius. Now you have a huge surface area for the typical particle around 200 meters square per gram. Now, what we wanted to do is just having the nanoparticle is not enough because they are so fluffy, light in weight. The density, tap density is very important in the battery. You have to accumulate a lot of material in a smaller pack. So we started heating those particles to higher temperature. So the surface area went down because particles got sintered to each other. So namely, if I have a 10 nanometer particle and another 10 nanometer particle is connecting to that, so some of the surface area is lost. But at the same time, there was a reorganization in the particle because of the sintering. So particle came together, but then because of the moment and sintering, there is a cavity. And that cavity was the important thing for us. Although the surface area was low, but when you bring lithium back and forth, there is little bit expansion happening. So the alloy team forms with lithium is lithium 4.4T. And when you see structurally, it is almost 300% higher or three times bigger particle when lithium reacts with T. So we have to accommodate that expansion in some cavity. And that is why purposefully those cavities were created in the electrode architecture where the lithium could come, expand in the electrode without expanding the whole battery. Within the electrode, it was happening locally. And then the battery charge and discharge could happen. And that's the reason you get longer life because of that expansion and contraction, which were attenuated or accommodated in the electrode itself. And that is the beauty of these interconnected particles, which provide a longer life compared to the nanoparticle, which can react very effectively with the electrolyte. And if the particles are just away from each other, even there is no electron hopping happening very effectively. So if the electron loss is happening, then instead of having the longer cycle life, you have a shorter one.
Okay, thank you.
You are welcome.
There's another question. Will the
Please.
excitation wavelength change the emission wavelength in the PL spectrum?
Is it the question from Jay Shankar?
No, from Danya.
Okay. So it could happen, and I think compared to me, Jay Shankar could answer it effectively. He is an expert on photoluminescence. So based on the excitation state, sometimes the emission spectrum could change, but most of the material has a fixed spectrum for D to F transition. So the spectrum should appear at certain wavelength, but because of the impurities, because of the excitation, because of small changes or doping, it could shift slightly, but there shouldn't be a dramatic change.
Thank you, sir.
Sometimes the intensity also can vary based on the material's architecture, material's particle diameter. Sometimes you can get very strong emission signals. Sometimes you get very weak emission signal. So different things could happen based on the impurities, dopant, excitation wavelength, and so forth and so on.
So
Any
one
other
more question. Yeah, yes, sir. Usually we cinder the material for the particular phase we require when the cavity is produced.
Mhm.
Can you tell any reference?
To make the cavities?
Yeah, when the cavity is produced.
I did not show you, but if you see some of our publication, can you still see the presentation?
Yes, 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 sir.
So this is an example that you do it at your home every day. We took wheat flour, the wheat flour that you make chapatis out of it. Wheat flour is typically a starch, and in that flour around 60% is water and remaining is carbon, hydrogen and oxygen. When you take this one and put it in the furnace or whenever you are cooking on the pan, what happens is a lot of fumes are coming out. What is that fumes belongs to? That is coming from the water. So you have a starch. In that starch, you have carbon, hydrogen, oxygen, and a lot of water molecule around it. So when water comes out of the system, it comes like a steam and steam pops. And that does create those cavities that you can see here. You see, such a beautiful larger cavities are created here. And those cavities are very important where the material or the electrode you want to make. And not only we made the cavities, we decorated those cavities with another new materials that allow to expand and compress. For example, it looks like a very big cavity with two small particles. In this case, if your lithium is coming in, it will expand and become a big particle, but it is happening within the cavity. So I used to call it as a carbon hotels. And the other particle are like a guest. So it is a host guest kind of thing. So the guest who comes and stays in your hotel can eat and become big, but the overall architecture of hotel is not changing. The total volume is the same. And with that, you see, we could put any particle from the periodic table, and you can find that in our different publication on web page, Viper web page that you can Google. So this is the material or series of material I was developing when I was in Japan, and that's why I have a Japanese patent on this one, where tin was accommodated in this one. You can take anything from the periodic table that can be decorated very nicely on the carbon architecture. And these materials are very inexpensive because the wheat flour is inexpensive. We take them and make chapati out of it, where you can mix that with a chemical precursor, heat it up, you get very nice core shell architecture, or you can get decoration. For example, here the gold particles are decorated on the surface of carbon to get the catalytic activity. Platinum is a catalytic material. So there are so many examples. I skip it because I wanted to give some time for you to ask questions. But indeed, beautiful materials can be created with very simple technique.
I would like to take this opportunity to thank our distinguished speaker, Dr. Vilas G. Paul, for his excellent and highly informative session. At the onset, I would like to thank you, sir, for accepting our invitation to be one of the resource persons for our international conference on nanomaterials. In spite of your busy schedule, you were magnanimous enough to make it available to spend your valuable time with us. We are indeed highly grateful to you, sir, for spending your valuable time with us. Sir, you drew us into a deeper knowledge of the fate of nanostructured materials in rechargeable batteries. Your lucid description on the lithium-ion batteries, that is the advantages, disadvantages, challenges, and the working of lithium-ion batteries is indeed highly appreciable. You have explained in a very clear way so that I am sure that the students have been enriched by your session. And you also explained to us the distinct way to synthesize the core shell titanium oxide carbon nanostructures. And you also explained the reason for using titanium oxide as an alternative negative electrode material. Each moment is a wonder. Each moment is full and complete. And each moment is a song of the divine. Yes, sir. You led us into the wonder of the energy storage nanomaterials. And zeal without wisdom is like fire without light. Your zeal and wisdom will surely motivate all the delegates who listen to you to do research in this excellent field of energy storage materials. On behalf of the management, principal, and the faculty members of the Department of Physics, I extend to you our heartfelt thanks for accepting our invitation and for delivering a highly informative lecture on these energy storage materials. Thank you, sir.
You are welcome and good luck.